Welcome to the SAMPE Q&A session for emerging materials and processes, and thank you all for joining. I would like to make you all aware that this session will be recorded and posted on the SAMPE website for on-demand viewing. If you have any questions throughout the duration of the session, please type them into the Q&A feature found on the control panel of the Zoom meeting window. My name is Andy Frazee, and I am a strategic research scientist at SAMPE in our Composites business unit. And I'll be leading the session today. So with that short introduction, I would like to introduce our four panelists for today. Panelist one is Anvesh Gurijala from Boston Materials, Inc. Anvesh is the founder of Boston Materials and the inventor of the SUPERCOMP technology. At Boston Materials, Anvesh has created the framework for the commercialization of SUPERCOMP products, from developing the necessary manufacturing technology, identifying the market opportunities, and building a network of customers and partners. He has a bachelor's and master's degree in mechanical engineering from Northeastern University. Anvesh's presentation and paper is titled Damage Tolerant Composites Reinforced with Z-axis Milled Carbon Fiber. All right, panelist number two is Boris Bulgakov from the Institute of New Carbon Materials and Technologies. Boris graduated from Lomonosov Moscow State University, where he was a faculty member in chemistry in 2009 and defended his PhD thesis in 2012. Boris is working in the field of heat-resistant thermosets for industrial applications at Moscow State University and the Institute of New Carbon Materials and Technologies. Boris is the leading researcher in phthalonitrile resins technology. Boris's presentation and paper is titled Advanced Phthalonitrile Resin Systems for Vacuum Processing. Panelist three is Zhe Liu from Florida State University's High Performance Materials Institute. Zhe has 10 years of polymer and composites experience developing carbon nanotube, carbon fiber reinforced thermoset, and thermoplastic composites, especially as high temperature applications. Zhe's paper and presentation is titled Lightweight and Flexible Thermal Protection Systems for High Temperature Composite Applications. And panelist four is Julie Roark from the University of South Carolina. Julie is a master's student at the University of South Carolina. She is continuing her education, graduating in the spring of 2020 from the Engineering and Computing College with a degree in mechanical engineering. Her passion for the past 2 years has been studying the response of composites through low and high velocity impacts. Manufacturing the composites panels with the automated fiber placement machine and the high velocity impact experiments were her favorite parts of this project. The title of Julie's presentation and paper is High Velocity Impact Response of Hybrid Pseudo-Woven Fiber Reinforced Composite Laminates. So these are our four panelists and their backgrounds and their presentation titles. At this point, what I'm going to do is start with panelist number one, and I have some questions queued up that I'll start asking each of the panelists. I'd like to remind you again that while we're going through these questions, please remember to add your questions in the Q&A feature found on the control panel of your Zoom meeting, and I'll be sure to ask those as well. All right, so let's start with panelist one, Anvesh. Your first question that we have here is, how much control do we need to have in the milled fiber length, and what is the fiber length?
Thanks for that question, Andy. So maybe I can answer this question while showing something on my screen. So I'll do that right now. So the question was, how much control do we have on the milled fiber length, right? And basically, and what we're using today. So what I'd like to show you is a video of our fiber alignment process today. We use milled carbon fiber from commercially available sources. Anywhere from 50 to 200 micron is the kind of the optimal fiber length. Our standard products today use 150 micron fibers. And so there is some polydispersity in the fiber as we receive it, but we have a coating process to kind of cope with that polydispersity, and we actually get within 3% areal weight distribution of the FAW through our process.
All right, thank you. Go on to panelist number 2, where panelist 2, Boris. First question that we have here for you is, why do you think thermal oxidative stability and flexibility was improved by the addition of the phosphate linkage?
Like phosphates are known as antipyrines, so it's kind of some typical molecules, kind of thioxylene phosphate or something like this, which are used for these purposes. So also we made the tests of our materials, and they exceed by thermal oxidative stabilities over phthalate with no phosphates. And about flexibility of phosphate linker, it's, the TG of these oligomers told us that they're more flexible, basically, that the aromatic ones.
Okay. Could you remind everyone what the control was as compared to the phosphate linkage?
The control was TJ, so we made a TJ analysis, and during the same experiment, the rate of combustions of the polymer containing phosphate bridged monomers were much less. And also made some tests on limited oxidant index, which are also like the results, the LOI for phosphate containing polymers were much higher than for just carbohydrate polymers.
Okay, thank you. All right, panelist 3, Zhe. The first question we have. So the first question we have for you is, why did the high carbon nanotube concentration decrease in strength so drastically after 5%?
Yeah, first we want to choose optimized phenolic resin solution to make the carbon nanotube and phenolic composite. So we tried the different concentration of the solution. So after 5% of the phenolic weight percent solution, there has some resin-rich area, like because the carbon nanotube network has a very small, tiny, nano-sized parallel structure for the carbon nanotube network. And after 5% phenolic resin, the resin-rich area from the surface of the carbon nanotube will just break first, then our nanocomposite will break. So our optimized concentration is 5%.
Okay, great, thank you. So panel 4 is Julie. Julie, the first question we have for you is, what is the projectile made of in your testing, and what is its weight?
Yeah, so the projectile is composed of 2024 T351 aluminum, and it's a thin-walled cup-shaped projectile that has a defined front face radius of it, and then the weight was 50 plus or minus 0.5 grams.
Okay, and in this test, does this projectile mimic something that could be encountered during like routine operation of materials?
It does. We've mimicked birds or rocks, and basically any ballistic impacts, such as bullets or debris, anything with a small diameter that induces a circular impact zone, which was intended for the impact on applications such as engine fan containments and open rotor engine blades.
Okay, great, thank you. All right, so let's go back to Anvesh. Anvesh, the question we have here for you is, how does viscosity affect the orientation during processing? And will thermoplastics impact this more than epoxy systems?
Andy, yeah, thanks for that question. So again, I'm going to share my screen so I can show some pictures. And the question was, going from a thermoset epoxy with low viscosity versus a high viscosity thermoplastic, is there any difference in our processing? And the answer is no. So we use a water-based slurry coating process to align the fibers on various substrates and films. So here I'm showing on the right-hand side a 3K carbon fiber fabric that has the Z-axis milled carbon fiber. And we stabilize this as a dry reinforcement. So it has like a very trace thermoplastic binder, so you can actually handle it just like a dry fabric. And then we prepreg that with a thermoset epoxy, so like a hot melt epoxy. So for our work with thermoplastics, we processed polymers such as PEI, so all-temp, polycarbonate, PEEK, some pretty high viscosity resins. What we do is we actually melt and fuse a thermoplastic film into this dry carbon fiber structure. And some of the new work that we're doing, we're actually coating thermoplastic films with the Z-axis material as the dry stabilized coating. And then we can actually infuse the underlying thermoplastic film, which we use as a web in our process, into the carbon fiber matrix, if that makes sense. So really no issue with thermoplastic viscosity.
Really interesting. Thank you. All right. Boris, the second question that we have for you is, at what temperature were prepregs produced in your work?
Okay, thank you for the question. The prepregs were produced at 120 degrees Celsius. I can show you this. Like this is a viscosity profile of our resins, and so about 120 degrees Celsius, there is a viscosity low enough for a good impregnation of the fibers, the fabric, in this situation of, in the case of our prepregs. So, and it's a kind of convenient temperature for working with the prepreg machine. So higher is not very nice, but kind of 120 is more than affordable. Yeah, and actually I want to also add an illustration for previous questions. I have graphs of TJ, so you can see how the combustion speed is lower for a molecule containing phosphate bridge over the one with no phosphate. Yeah, thank you. And also, I want to question that doesn't concern this. I can't find the option questions and answer option in the Zoom. It doesn't work, so I can find it, but it doesn't work. Is it okay?
Okay. Okay.
So maybe you should activate it for me or something, but I can't put anything.
Well, there aren't any questions, any new questions just yet.
No, there is no. No, I have questions with other participants, so.
Oh, okay.
Ask them later.
And
yes.
I think, Boris, you can put those in the chat feature. Are you able to use the chat feature?
Yeah, of course.
Perfect. Go ahead and use that. As a panelist, it disables the Q&A for some reason. So go ahead and just stick your questions in the chat, and Andy will get to those.
Oh, okay. Thank you.
Thank you. I'm glad you have questions.
Yeah, thanks, Boris.
Yeah.
Okay, while Boris is putting those questions in, I'll go on to Zhe. Zhe, the next question that we have for you is, did you test the interlaminar shear strength of the bonding layer between the two material systems?
Okay, let me answer this question. Can you guys see my share screen?
Yes.
Oh, yeah. Actually, we didn't test interlaminar shear. So for composite ASTM standard to test interlaminar shear, the sample thickness around 6 millimeter. So for our composite, the thickness only 1 millimeter. So instead of using interlaminar shear, we tested combine the coefficient of thermal expansion to check if there's some delamination with temperature going up. Also, we test the mechanical property of the composite using the 3-point bending. First, the coefficient of thermal expansion. So if there's very weak bonding surface between our thermal shielding layer and the composite, so with the temperature going up, there might have some break or delamination between the bonding layer and the substrate composite. And we test the CTE to know the coefficient or the expansion of the composite through the in-plane direction and through thickness direction. And from the both result, we see without the thermal shielding layer, and the composite CTE is going up with the temperature going up. That's because the polymer chain just have more movement space after the TG. And with our carbon nanotube shielding layer, we can see from the figure, left is the through thickness CTE and right is implant. So for both direction, we can eliminate, reduce the CTE to almost around 0. That means we have a very good bonding between the shielding layer and the composite. Also can limit the expansion space of the polymer chain. And then we tested the 3-point bending for mechanical property with this thermal shielding layer and without this thermal shielding layer. For the first coupon here, which is without thermal shielding layer, we can see this mechanical property around 1000 megapascal. This one is our baseline. So after we calculate the 3-point bending strength with the shielding layer, the mechanical property can sustain around 94% compared to the baseline. There's a little bit drop because we calculate the thickness of the shielding layer into the calculation. That means our sample is thicker than the baseline. So if we compare the force, they should be same. Yeah, that's my answer.
Great, thank you. All right, so Julie, the next question that we have for you is, how many shots were taken for the V50 calculations?
So yeah, for the first panel, we only had to take 4 shots. For the second panel, we took 5 shots. And for panel 3, we took 3 shots. And actually those values gave us the V50 calculations that we were looking for, with 2 panels only having the penetration, which was the panel 3 and panel 2.
Okay, awesome. Well, thank you. Okay, so we'll go back to Anvesh. Anvesh, what would you say was one of the most surprising or interesting discoveries with your work?
Andy, yeah, thanks for that question. I mean, the whole thing was very exciting, but I would say the highlight was, you know, typically our process was taking a continuous fiber substrate. So when we first started, it was like a unidirectional dry tape, and adding the Z-axis fiber as a surface coating. And what we found is like we're basically inherently tied to the property of the underlying tape or substrate. But through our work, what we have done is actually we shifted some of our processing to actually coating a thermoplastic film. So we can actually use that film as a release liner. So we can actually create a standalone Z-axis material. So that has a tremendous scope of applications by itself. But then we can also now integrate that to off-the-shelf unidirectional prepregs, both thermoset or thermoplastic. And that really opens up the scope for Boston Materials on kind of the applications we can deliver products into. And now we're actually looking into using the Z-axis fiber as like a microcore material because it's, you know, very thin, like 150 microns thick. So we can create really thin laminates for like consumer electronic devices or even metal fiber laminates as well. So a lot of opportunities have opened up as a result of kind of this work that we presented during the paper.
Okay, great, thank you. All right, so let's go move on to what do you see as the future influence of your work from this project?
Excuse me, it's a first question for me, right?
Yes.
Just get a bit distracted. I think the future influence is already kind of starting because we're already testing our materials for applications in engine constructions, for example, with Safran company and some Russian engine developers. And I think in general, our work can extend the temperature range of operation for polymer composites. So, and I think at some point it will work. Yeah.
All right, thank you. Zhe, the next question that we have for you is, did you study long-term aging of the covered materials at low temperatures? For example, like 300 to 400 C?
We didn't check the long-term aging of the covered material because for our hybrid material, we use BMA carbon fiber as our substrate composite. So 300 to 400 degrees C already higher than the TG of the BMI resin. So it's a good question. We can study the long term for only the shielding layer, carbon nanotube, and phenolic resin itself. So carbon phenolic resins decomposition temperature around 5 degrees Celsius. Yeah, so 300 to 400 looks like a promising temperature, I think. Yeah, we
Okay.
can do in the future.
Great. And then could your materials be used to cover corners or other complex shaped composite parts?
I think it can use for complex shaped composite part because our shielding layer itself is only 100 micron. It's very, very thin layer. It's very flexible, and we cured for the first cycle is curing the carbon nanotube and phenolic resin to making this shielding layer. So after that, it's still very flexible. So for composite manufacturing, we can just put this top layer on top of the prepreg and put into the autoclave. So if the structure is complex, we can still using this very flexible thin layer on top of any prepreg. Yeah.
Okay, thank you. Julie, based on after your conclusion slide of your work, what do you think are the next steps for your work or your research?
Yeah, I think the next steps, we had some issues from our autoclave and the operators curing issues from our autoclave as well, and we've been troubleshooting those. I think the next step is to get more values, to get a exact value of the V50, which we found. And we found by the few tests, but we would like to expand our horizon of testing and the amount of tests that we've done, and get some more panels, different orientations of the panels in there, and compare those panels to the ones that we have and the values and data that we already have. But the more experiments would be better for us.
All right, Anvesh, the next question we have for you is, how do you see the future influence of this project?
Yeah, Andy, so that's moving forward with this project specifically. We are looking into creating organosheet materials, so really thin organosheets where we can replace 33% of the continuous carbon fiber with a recycled fiber, low-cost recycled fiber, to not only bring down the overall cost of goods of the organosheet, but also utilizes the Z-axis reinforcement to tune different RF and thermal properties, and also see higher damage tolerance like we presented in the paper. So the next step is really going from this material level characterization to actually a part level characterization, such as like a laptop enclosure, and produce more data on thermal management applications and more direct impact applications as well that you typically see consumer electronic manufacturers perform on their products.
Okay. Boris, so the next question we have for you is, what would you say was one of the most surprising or interesting discoveries with your research?
I don't know. Hard to answer this question. I think how I really don't know. What was the most surprising? I think I may say it was something exciting that our ideas worked like what we planned. It somehow in reality appeared to be almost the same as we planned. So And for me, for a personal experience, also how many consequences it brought. I mean, the problems with, not the problems, it's and pleasure problems, how to settle out, up and so on the material. So new experience and a lot of exciting things connected to this mostly, I think.
Okay. So Zhe, what would you say was one of the most surprising or interesting discoveries with your work?
First, I think our shielding layer. Yeah, our shielding layer is very thin layer and is very robust with all the surface of the composite. We can develop more with the other substrate composite. Also, like long-term stability of the thermal shielding is another thing I want to know more. And one promising is we tested for very high temperature using the propane torch to burn the composite. And it can give us a very excellent result. Also, we developed all the mechanical property, including the three-point bending, CTE of thermal expansion, and thermal conductivity of the composite. The shielding layer also can lower the thermal conductivity through the thickness direction. So I think this anisotropic structure of carbon nanotube for very high thermal conductivity implant direction and very lower thermal conductivity through thickness is very interesting property. We can develop more from this direction.
Okay, thank you. So Julie, how do you see the future influence of this project?
I see the future influence being able to control the damaged area and contain that damaged area into one specific spot to where the impactor struck the composite part. So I think the future of this project would be containing that damaged area and controlling that area of damage.
Okay. Any ideas on how you might approach that?
Exactly what we're doing with the high velocity impact, the different panels and the different orientations of the panels is showing us on the outside of the strike face of the panel, the containment of the damage once it's struck by the projectile, and it's showing us which panels contain that damage better for each different composites.
Okay, interesting, thank you. All right, Anvesh, last question that I have for you is, what are the next steps for your work?
Yeah, so that's a good question. And it kind of links back to the first or second question. You know, we have products in the market today with epoxies, and we're getting into new products with tooling, with high temperature epoxies. But really, the growth opportunities for us are in thermoplastic composites. And so this is where we're taking what we have already developed with epoxies, but now implementing polycarbonates, PEEK, Altem, even some PAKE materials. So that's really what's in the future for Boston Materials. Looking at some hybrid overmolding, automated tape laying practices with thermoplastics with our Z-axis reinforcement is kind of what's exciting and new for Boston Materials.
Great, thank you. I'd like to remind everyone as we're going to the final set of questions, we still have plenty of time. If you have any questions, you could add them to the Q&A at the bottom of the control panel of your Zoom window. All right, so Boris, what are the next steps for your work?
The next step is completing with like starting mass production and enlarging our market perspectives through European and other Western countries.
Okay.
Things like this, yeah. And also now we are working on, we have prepregs and vacuum infusion or RTM resins, but we also want to expand our technologies and our abilities to make our prepregs more pliable. I mean, like that's kind of to ease their to deploy at room temperatures and so on, because the most problem is now that we need preheated rooms for our prepregs to make a complex shaped parts. So I think this is the direction of the future, to ease the use of our materials for the customers.
Great, thank you.
Yeah, thank you.
And Zhe, last question for you is, what do you think the next steps are for your work?
My next step is continue to develop the new thermal shielding layer, even increase thermal stability and increase thermal protection for the beneath composite. And we have some preliminary results with some method can continue lower the through thickness thermal conductivity, also maintain the good mechanical property of the composite. And also I might develop more for the resin matrix for thermal shielding layer. We know the phenolic resin is not some structured resin used. It's very brittle, and we can develop some thermoplastic with continue give us a good mechanical property and also good thermal property. Yeah.
Okay. All right, thank you. So at this point, I think those are all the questions that we have. Like to thank everyone for participating in this session. And if you have any additional questions, feel free to fill out the form on the track landing page on the SAMPE North America website, and SAMPE will follow up. Make sure to check out the content being released next week for the manufacturing technology track within the virtual series. Thank you, everyone, and have a great rest of your day.
Thank you.
Thanks, Andy. Thanks. Bye.